In this one, let's understand correlation in clear detail. Now, one thing that you must understand is correlation is a bivariate analysis technique. That means in order to compute correlation, you need to have two different variables. While other metrics such as mean, standard deviation, coefficient of variation, and so on, these all requires only one variable in order to be computed. Whereas in order to compute correlation, you need two variables. And that is why it is also considered as a part of bivariate analysis technique. So in this video, we will see everything about correlation, starting from what is correlation, the intuition, when and when not to use it, the formula, computations, and there are other types of correlations also. There is not just one single formula for correlation. There are multiple variations of it. We will explore that in brief. We won't go into the details of the other types of correlation, which we will not cover here, but you will get an idea of what it is about. Let's get right into it. When someone uses the term correlation, what they typically are referring to is the Pearson's correlation. There are two other forms of correlation, we will get to that later. But what you see here is the formula for Pearson's correlation. Now, this may seem a bit complex. I will walk you through this shortly, but here the top part in the numerator is also called the covariance of x and y. So what is happening here is, given two variables, say you have variable a and b, you have certain values over here, b also have certain values over here. You have the mean of a as a dash and mean of b as b dash. Now from every value of a, you subtract a dash. So I am calling this number 1, this is number 2. Let me write it as 1, 2, 3, and so on. From every value in a, you subtract the mean of a. Likewise, in every value in b, you subtract the mean of b. That is what is written out over here. Then multiply both of them and do a summation. I will walk you through this process in more detail. Now, this whole summation is called the coefficient of variation. Whereas there are two terms over here in the bottom. The first term here is the standard deviation of x, the first variable, and this term is the standard deviation of y. What this means to us essentially is correlation coefficient is nothing but covariance of x comma y divided by standard deviation of x, standard deviation of y. This is the formula for correlation. Or to be more precise, it is Pearson's correlation. Now, this correlation value can vary between -1 to +1. It is always between -1 to +1. And what does this mean to us? To understand that, we need to understand what correlation is in the first place. What does it actually represent? Now, correlation is supposed to measure the degree of relationship between two variables. To be more precise, the degree of linear relationship between two variables. Now, here we have two variables, the discount and the sales of a particular product. This product typically is an essential commodity, and if you can see, as you increase the discount, the sales also increases. If you plot these points over a scatter plot, the discount is on the x-axis and the sales is on the y-axis. As you increase the discount, the sales is also increasing linearly. So in this case, you should expect a very high correlation. When I say very high correlation, a correlation very close to 1, +1. To compute correlation in Excel, the function that you would use is correl. Select the two variables for which you want to measure the correlation. So you have a 0.97. It is almost close to 1. A very high correlation is observed. Now, when do you see a negative correlation? If the relationship is opposite. So in this case, as discount is increasing here, the sales is going in the opposite direction. It is evident from this graph. As the discount is increasing on the x-axis, the sales is going down. So if you compute the correlation for this, you can expect a negative number. It's almost perfectly -1. But what if you don't see any continuously increasing or decreasing relationship. Suppose if you see a shape like this, it is increasing to a certain extent and after that it is decreasing. This is possible for an essential utilities. For example, for certain commodities, if you give discount, the sales will increase. But then if you give too much discount, it will lose value in the eyes of the customer and your sales will drop. So this is possible for such commodities. If you try to compute the correlation for this, I would expect a weak correlation over here. It's a weak negative correlation. On the other hand, if you compute the correlation in a split manner, suppose for this region, I'm going to compute correlation, one correlation, and for the rest of the region where it is decreasing, I'm going to compute a different correlation. If I do it that way, you can see a clear positive and a negative correlation. So the correlation of the points from 60 to 90, it is clearly negative. On the other hand, from 10 to 50 where it is increasing, when the sales are increasing, it is a high positive. Now notice here, even though this number could have been well close to 0 also, this could have been 0.1 or this could have been point minus 1 or this could have been point not 5. It could have been a very low number. Now the point you need to take away is, even though these two variables are not correlated, there is a significant and clear pattern between the discount and the sales. That sort of pattern will not show up in this type of a variable because their relationship is not entirely linear. It is piecewise linear. When I say piecewise, here this piece is linear and this piece is linear. So you need to take these two separately. You need to separate out these two segments and compute their correlations. From that, you will be able to tell whether these variables have some sort of relationship or not. So in this kind of a case, computing correlation entirely will not work. All right. Whereas in the first two cases where the dependency is clearly linear, in those cases, it is perfectly fine to compute correlation. These two cases. All right. So what happens if these two are not related at all? For example, in this case, the discount is increasing, but if you look at the values of sales, it is increasing and decreasing. There's no relationship. So if you look at this graph as well, right, it is like horizontal. It's not moving in a certain direction. Now, in this case, you should expect the correlation to be almost nearly zero. Hope that is clear. Now let's see how to compute correlation. Here I have taken two columns from the empty cast dataset. We have seen the empty cast dataset multiple times. So this dataset is a built-in dataset that comes with the R programming language. You can find it on Google as well. If you search for empty cast dataset, you will be able to easily find this dataset. Now from that dataset, I have taken two columns, the mileage of the cars and the weight of the cars. Now I want to compute the correlation between MPG and weight. How to do that? If you remember the formula, covariance of X and Y divided by standard deviation of X and standard deviation of Y. This is the formula for correlation. Now to compute the covariance, so how do we go step by step? So the very first step is from each value of MPG, subtract the mean of that column. Likewise, from each value of weight, subtract the mean. So this is nothing but B2 minus the mean is B35. I have done the same for all the rows over here. Same applies for column F as well. That is the weight minus the mean of the C column, weight column. Next step is for G column, you just multiply this and this. This is to compute the covariance. The covariance value comes from the product of E and F. This is for covariance. Now, these two columns is nothing but the square of this and the square of this. That is E power 2 and F power 2 is these two columns. So after doing the computation of all these three, I am summing all of them up. Now take this to the numerator divided by these two to the denominator. That is what I have done here. G35 divided by H35 product of I35. That is nothing but the correlation. Simply you can compute it in Excel like this. Now one key thing to be very aware of is correlation does not mean causation. You would have come across this term a lot across various data science or data analytics blogs. Let me talk about it a bit more. Now, if you think about these two variables, the mileage and the weight of the car, you can intuitively understand that if the weight of the car increases, the mileage comes down, right? So you need to apply the thought behind that, the business understanding or the logical understanding behind it to make an inference on whether a particular variable is influencing the other or not. Though correlation is a measure of linear dependence between these two variables. For example, here I could have one more variable, for example, the weight of the owners of the car also, right? The chances that could so happen that there is a particular sample in existence where by increasing the weight of the owners, the mileage of the cars is also increasing or decreasing or any other way, right? It does not mean that the weight of or whatever variable is it of the owner is affecting the mileage. In fact, the weight of the owner could also affect the mileage because if he is sitting on the car and driving the car, then that can in turn affect the weight. But that is not the point. You can come up with n number of rubbish variables that are accidentally correlated with the mileage of the car. That is still possible. So what that means effectively to you is whenever you are seeing a high correlation between two variables, do not take it at a face value, but go behind the meaning of those two variables, what they stand for, and then make your inference whether the two variables are influencing each other or influencing one way or not. So I also mentioned about two other correlation metrics. What we have been discussing so far is the Pearson's correlation. There are two other types of correlations at least. The second one is Spearman's rank correlation. I will talk about the intuition of this briefly. The third one is Kendall's correlation. This one will require a completely different video altogether, but let's understand the concept behind Spearman's correlation. The concept is instead of using the raw values that are listed over here, if you replace these variables, these values by the rank of the variable. When I say rank, for example, the lowest value in this variable, say 15, if 15 is the lowest, I will assign it a rank of 1. The next higher value or the next lower value is, suppose if this is the next lower value, this will get a rank of 2. Likewise, whichever is the highest value, I think 30.4 is the highest. There's a tie between these two 30.4s. Both of these variables will get a rank of 32 and 33, the highest rank, right? Likewise, convert the second variable, that is weight, also into rank and then compute the correlation like how we did. Now that is called Spearman's rank correlation. That is the simple funda behind it. So now you know what is correlation, the different types of correlation, the intuition behind it, the formula, the computation, and when not to use it and how to interpret it. We have seen all of these things in this video.